Okay, it's been recorded right now. Amir Akasha kena tendang masuk balik Okay, we look back at the fundamentals of proving a little bit. We already learned about direct method, indirect method, contradiction method. I said I skipped at that time because, like I said, I do not really want my student to focus, but I teach it in my video lecture. Today, what we're going to do is to apply direct method. Recall back, direct method follows modus ponens, where you start with P implies Q, you try to prove P is true, then as a conclusion, Q is true as well. Hence the name direct method. So last week, we already know how to prove for even and odd cases. Then today, we will focus on number theory, a different kind, not even and odd, different. For example, okay, I open back number theory. This theorem. Okay, we have three theorems there. The first one, the second one, and the third one. I remember that I skipped this because I say I want to focus on the proving. For example, we start with number one. You have a theorem. If let three integers, okay, A, B, C be integers, then if A be well, such that, okay, I restructure back the question, it's the same. If A is a factor of B and A is a factor of C, what will happen, the implication is that A is a factor of the summation between B and C. The first challenge for you guys is to understand first what this theorem is all about. For example, as shown in here, example A kat bawah ni, if 3 is a factor of 9, and 3, which is A in this case, okay, I show you. Let A equals to 3, B equals to 9, and wait. Oh, no, B equals to 9, C is 15. This theorem indicates that if 3 is a factor of 9 and 3 is a factor of 15, of course, then this will happen. Then 3 is also a factor of 3 plus 15. Is it correct? If we check, 3 is indeed a factor of 18. This happens to be true for every integer. But the thing that is being shown here is not a proof. It's just a theorem which has already been proven to be true. Right now, for you guys and girls, I want you to know how to show that this statement is true for every integer out there. Okay, but again, like I said, it's important for you to know, to visualize what is the use of this theorem. This is one of the small example. Okay. I write back. Okay. The previous example last week, we know that if we want to prove even and odd cases, you need to know the definition of even. The definition of even is the multiple of 2 or 2k, such that k is an integer. For odd is 2k plus 1 or 2k minus 1. For this time, we cannot use that definition anymore because this is not an even and odd cases. It is based on divisibility or factorability. This is the definition of divisibility. Definition. I start with the definition first. I will use another alphabet so that you will not be confused with the top representation of alphabet. Divisibility means is that if x is a factor of y, then it means that y is equal to x times z. This small z is an integer. We will use this kind of definition afterwards. So recall back. If x is a factor of y and y is also a multiple of x, then it means that y can be made as a linear equation between the product of x and z. And that z must be integer. Just now, we say that 3 is a factor of 9. Is it true? If 3 is a factor of 9, then it means that 9 equals to 3z. This z must be integer. And based on your knowledge, you know that 9 equals to 3 times 3, and 3 is an integer. So that's why 3 is a factor of 9. That's why 3 is also a factor of 15. And 3 is also a factor of 18. You can prove it on your own. Huh? It's very simple. Right now, we will use this definition to prove the top theorem. We start with the first indication here. This is the P, A, B, and AC is the condition. This is the implication of the condition, conclusion. I will start first, like this. If A is a factor of B, then I believe that B can be made as A times, dah ada A, B, C. J lah boleh J. J. This J must be integer. Right now, I have two conditions. A is also a factor of C. That means C can be made equal as A times K. This K is also an integer. We proceed with the next line of the idea. We need to prove that this A is a factor of the summation between B plus C. What is B is AJ, C is AK. Therefore, B plus C is equal to A times J plus A times K. This time I will factorize A, becomes J plus K. J plus K. The proof is not complete yet. It does not make any sense for the time being. Right now, J is integer, K is an integer. Integer J plus integer K will be another integer. Let's say L. L is J plus K, and this L is an integer. Right now comes the moment of this proof. A is a factor of AL. In this part, some of the students cannot visualize this. Why suddenly A is a factor of AL? I can show you a small proof here. Why A is a factor of AL? You look at this example. This is not a proof. This is just a visualization of the example of the proof. 3 is a factor of 3 times 5. Correct or not? Let's say A is 3, right? This is A, this is L. Actually, I take another example. Just now is the summation is 18. Okay. Just now, 3 is a factor of 18. 3 is also a factor of 3 times 6. Try to look left and right now. Suppose that A is 3, L is 6. Therefore, AL is equals to 18. L is 6. A is 3 lah. That's what happens here. To justify this is that A is definitely a factor of a multiple of A times some integer. This is what happens here. As my conclusion, big conclusion, AL ni apa? AL is B plus C. This is what happened. I recap back. The proof is now complete. We start with the implication here first. Suppose that we believe that A is a factor of B and A is a factor of C is true. By using the definition of divisibility, B equals to AJ, C equals to AK, then I sum up. The idea is I sum the B plus C. And this B plus C can be made equal as the product between A and L. And as A is a factor of the multiple of A, which is AL, this AL is equivalent to B plus C. The proof is complete. Please, if you have any question about this theorem and its proof, you may ask right now. Okay, no question. If no question, I will proceed with the next theorem. We take the second one. If A is a factor of B, this one is short. Only one condition. If A is a factor of B, the implication is that then A is a factor of B times C for every integer C. The same manner, I will use the definition of proof first. If you look at the previous last week example and today's the first example, usually proof can start with by establish a definition first. You can start by that. So that's why sometimes definition you must memorize. You must know how to represent your definition correctly and know how to apply it. Right now, if A is a factor of B, then I believe B equals to A times J. J is an integer. This is B. What is BC? It becomes A times J times C. And as C is also an integer, J is also an integer, BC can be made as A times K. Ini bukan K. K. What is K? K equals to JC. And K is an element, which is an integer as well, because integer times integer is integer. And then I will get this statement, A is a factor of multiple of A. This is my idea. And as A is a multiple of, A is a factor of AK, and vice versa, AK is a multiple of A. What is AK again? AK is BC. This is how I complete my proof. Very simple. Because from the previous motivation of proof, I already know, A is a factor of a product of A. This line is very important. The top line is just by establishing the condition by using definition. This is the idea and this is the conclusion. Condition by definition. I establish the definition. This is the main actual idea. Then I finish with a conclusion. Do you have any question? No. Okay. Kalau ada cakap If you have any question, please do so. You can prove many theorems, but please be sensitive with the nature of the theorem. For example, some of the common mistake from my student, this is a divisibility kind of theorem, but you use 2K, which is an even and odd style of problem, which is not really appropriate here. Perfect square, last week, perfect square. Also, it's not appropriate here. Must understand first the question, theorem tu. Okay. I will proceed with the last theorem. And if you have the idea, please try to prove this on your own first. Okay. But you'll get already the idea right now, right? If A is a factor of B, the question right now, if B is a factor of C, the implication is that then A is a factor of C. For some of you guys who already have this idea, please jot down, please write down the first step that you need to be done. That you need to do. My grammar pun lari. What is the first thing? If I say that you, okay, prove this. What is your first line of statement that you should do based on our previous experience with the two examples just now? Buat I will catch you. Don't only listen. Sometimes you need to create your writing of the proving on your own back. The common mistake for my student and even myself, when I learned proof previously in my bachelor years, I memorize it. It can be done, but it's quite dangerous if you try to memorize the proof. It's really easier if you understand the theorem and how to manipulate, not manipulate lah, manipulate is quite a strong word, how to apply the definition to prove the theorem. That will be much easier actually. You can memorize, some of my students will memorize. Apa ni? Oh, someone share this. Thank you Shadow dalam WhatsApp. Nanti saya baca. Okay, I finish this one first. Okay. The idea is right now, the proof starts now. If A is a factor of B, then I assume that B equals to AJ. This J is an integer. I have two conditions. B is also a factor of C. C can be made as B times K. K is also an integer. What is C? C equals to BK, right? BK. And if you take the B from the top, C is actually also A, J, K. Ahli jawatan kuasa. As J is an integer, K is also an integer. The product of integer J and K will be another integer. Let's say L. This L is also an integer. As A is a factor of AL, and my conclusion, what is AL? AL ni, C. A is also a factor of C. The proof is complete. Now, it seems that actually it's not really that hard to prove the theorem of divisibility if you know the know-how. Now I open to the question. Okay, I would like to request something, sekejap. Because when I talk to my friend about online class, they say that the student is not responsive. But that's fine. I know I don't really push you to this. But he advised me that because his class, he asked the student to on the webcam. Okay, dia cakap, okay, why Adam, you talk alone, you will be quite lonely. Why not you ask them to open the webcam? So right now, could you just please me a favor? To those of you who can open the webcam, try to show your face for 10 seconds. Saya nak tengok jap. Saya nak tengok situasi yang mana tengok muka korang. Oh, thank you Pravin. Bukanlah lama sikit. Tengoklah, saya nak tangkap gambar. Oh, ada lagi tak? Saya nak tangkap gambar ni. Seriously, saya nak share dalam group. Oh, okay deh. Thank you. Nanti saya share. Oh, semua buka. Oh, kemarin. Oh, Farhan mana? Oh, Farhan mana Farhan? Oh, Gavin. It's so nice. I can see your face. Masya Allah, Badri baru-baru tidak ke? Oh, it's nice to see your face. This is the face of my student at their house. Tak payah buka mic, tak apa. I just want to see your face. Macam mana nak tengok semua orang? Boleh ke tengok semua orang? Kejap saya tengok setting. Bukan kan? Macam mana nak tengok semua orang? Muka ni rekod ni. Kejap. Macam mana nak tengok semua orang? I don't know. Saiful Azani. Sekejap. Oh, Saiful tak tunjuk muka. Okay, fine. Alamak. Saya nak tengok semua orang balik. Sorry I'm quite a noob. Noob bahasa dia. Change layout. Auto tile. Tak noob sangat Okay, this photo will go to WhatsApp now. Thank you so much guys. Okay, seronok tengok muka korang. Rasa ada communication lah juga. Okay, thank you so much. Boleh tutup balik. Okay, we'll proceed. I read the first, the one that your friend share from Shadow. Setakat ini bagi pelajar tahun akhir, final masih digambar untuk buka kemungkinan kita final di pekan. The Dean, okay, beberapa hari sebelum kuliah semester depan bermula, akan dibuat 1 minggu sebelum buka semester, pelajar akan pulang awal. Okay, thank you so much, Shadow. Alright, we proceed with chapter 2. No, still chapter 1. In terms of modular, congruent. Okay, this question is not available in the notes, so you can take the idea here. I clear first the canvas. Okay, I think I asked this in some of the assignment previously, but it's good for me to teach you as well. If A is congruent to B, mode N.
So, share screen.
Yes. Oh, sorry. Share screen. Present now. Entire screen. Okay, coming kejap. Okay. If A is a congruent to B mode N, A is an integer, B is an integer, of course N is also an integer. Then it also known that B is congruent to A mode N. Okay, this is a theorem that you will learn how to prove. I open this slide because this is the definition of congruent. If M is congruent to R mod N, at the left node, then it means that N is a factor between M minus R. Then I will try to apply here. Okay, if A is congruent to B mod N, then it means that N is a factor of A minus B. This is the condition. How to prove that B is also congruent to A? This is really interesting question at that time. I don't ask this during your assignment this time, but I want you to learn the knowledge. Okay. A minus B is an integer. A minus B. Let me show you this. Is N, if I negative this thing with A minus B, betul tak? Soalan dia lah. Okay. It means that what I want to show here is that if N is a factor of, saya tunjuk contoh betul lah. Just now you know that 3 is a factor of 18. Setuju tak? Okay, agree with me or not if 3 is also a factor of 18? Negative. Of course, right? 3 is a factor of 18. 3 is also a factor of negative 18. This is the idea that I implement here. As n is a factor of a minus b, n is also a factor of negative a minus b, which indicates that n will be a factor of b minus a as well. A very simple but clever idea on how to manipulate. As n is a factor of b minus a, therefore, conclusively it says that b also a congruent to a mod n. Very easy. Kacang. In English, we call peanut. Okay? You can take this. Take a look at this. How I manipulate the definition of congruent to apply to prove this theorem. Okay? It's always easy when you start with with the definition. Okay? I will open another topic. This is chapter 2. Chapter 1, I'll be verse 1 to chapter 2. It's opening, okay. In chapter 2, there is a proof of set, tak ada proof sangat. Ada sebenarnya, tapi ada jawapan di sini. So you can read this on your own later. I want to show this example. The longest chapter ever, set, function, and relation. It's about one-to-one. Mana one-to-one? Okay. Okay, to those of you remember one-to-one, one-to-one is that like this image on the left. This is a one-to-one function. I will start first with writing the definition of one-to-one. Fx is one-to-one if and only if Fx equals to, tak ada 4. If and only if Fx equals to Fy. Implies x equals to y. Okay. Right now I have the theorem. Contoh, proof Fx equals to x. Saya tengok mana soalan dia. Okay, this one. I just write it back. Nanti you can relate. 2x plus 2 is 1-to-1. Okay. It means Fx here will yield a unique answer, 2x plus 2. It means that if F1 dapat 4, okay, 4. Okay. F2 pula dia dapat 6, 6. So it means that there will never be an x which will produce Fx with the same value. Okay? Right now I want to prove whether this is 1-to-1. I will start first with this definition. This is the condition. Let Fx. Then apakah di Fx is 2x plus 2. Fy is 2y plus 2. Now goes to this part. If and only if 2x plus 2, I skip back a little bit. Fx sama dengan Fy, it means that I let 2x plus 2 equals to 2y plus 2. Right now, after some algebra manipulation here, the solution of linear equation, you can see that 2x equals to 2y, x equals to y. Therefore, it reflects back the definition. For this case, fx 2x plus 2, if fx equals to fy, 2x plus 2 equals to 2y plus 2, it implies x equals to y. As my conclusion right now, fx equals to 2x plus 2 is definitely proven to be 1 to 1. Very simple. I want to share some example which is not 1 to 1, like this. We know already, for example, if I let fx equals to x squared, this is definitely not 1 to 1. Why? Because if I put f1, it will be 1 squared equals to 1. If I put negative 1, it will be 1 as well. If I draw the graph like this, 1, negative 1, it will answer to the same 1. Therefore, this is definitely not 1 to 1. By the way, this can be a proof already if I write this nicely. Okay, I write this nicely, yeah. Okay, how to prove this statement? Actually, this already becomes the proof already, but not in a nice way. It's not according to the definition. The definition just now, if and only if fx equals to fy implies x equals to y. Right now, you see how to use this to be aligned with the definition. Okay, if fx equals to fy, like this case, f1 equals to f negative 1, right? But such 1 is not equal to negative 1. Based on the definition of 1 to 1 just now, if fx equals to fy, then x must be equal to y. But for this case, when fx equals to fy, this x is not equal to y. As my conclusion right now, if fx equals to x2, proven to be not 1 to 1. Okay, suddenly maybe some of my students right now will question me, why for the previous question we don't put example? Just now, this one, example 2 on the left here. Why I maintain x, why I don't put example f1 and 1? If you recall back my video lecture and also my online lecture, saya tak post lagi, sorry. Okay, video lecture, if for all, you cannot put example. You must put in a general statement, hence x and y. For this case, why I put example like this, or we call it precisely as counter example, because it is false. Bila false, when false, you can put counter example. This is false, right? Not. Then you can use counter example. Therefore, this proof has example of 1 and negative 1. For the previous proof of 1 to 1, there is no example of integer berapa tak ada. Any other question before I proceed to on to? No question, huh? Wow, so easy your online class. If face to face, I will receive 10 questions right now. But I assume that you understand. My wish is that you don't have a question. It's not because you don't understand. Actually, you understand. Then I will be more glad. Okay, if you know question, I will proceed first. If you have question later, then you can ask me later. We go to on to. I start with the question first. Proof fx 2x plus 2, the same as just now, is onto. Apakah dia onto? What is onto basically? Onto basically is that all elements of the codomain or set B in this example on the left is assigned by element from domain. Therefore, it's very important for me, for this question, I must write first what is the domain and what is codomain. Okay. Prove that fx equals to 2x plus 2 is onto. It means all codomain of integer is being assigned to at least one element from the domain. Like the diagram here. Okay. This one is onto, this one is not onto because y3 is not being assigned. That's why. But right now it involves infinite set here, Z. How to answer this cleverly is that I start first by understanding what is the definition of onto. It means that for every codomain elements, there will be an x from the domain such that fx equals to y. This is important. Every element from the codomain, there must exist some element x from the domain where the y is being assigned to it. Kena faham tu? I want to use the definition to prove this statement. So I will let 2x plus 2 equals to y because I assume y exists, right? Y. Okay? And because I said that y, the codomain is from integer, this y must be an integer. Then what is x? For this y, which is an integer, what is the value of x? Jadi, 2x, x equals to y minus 2 over 2. This is a very interesting question that I also forget. Is x an element of integer? Because I must prove that this z comes from this domain. Wujud tak x from the domain of integer such that this happens? Is this an integer? Fikir sejenak, saya pun lupa dah. Kejap. Okay. For this question, it might not be onto. Let me check. Is there, I start with this question first. Is there fx equals to 3? For this case, 2x plus 2. It means when I try to map this, this is fx, 2x plus 2. If this element exists here, what is the x? Ada tak? Is there exists such x which be assigned to 3? The answer is no, right? Let me prove to you. If y equals to 3, then 2x plus 2 equals to 3. This x is 1 over 2. 3 minus 2, 1 over 2. 1 over 2 is not an integer. It means when I list down every integer here, 1, 2, 3, 4, 5, sini pun 1, 2, 3, 4, 5, and until infinitely, 3 will not be assigned by any integer. So 3 ni tak ada kawan. Dia tak ada, there is no x which will be assigned to it. So as my conclusion right now, this is what I want to write nicely. If fx equals to 3, there exists, sekejap saya tulis balik. Okay, this may be much more clear. Fx equals to y, right? Ini dia. Let's say if fx equals to y, this y equals to 3. It means that if fx equals to 3, there exists no x from the integer such that fx equals to 3. There does not exist any integer such that fx equals to 3. As my conclusion, fx fz to z such that fx equals to 2x plus 2 is not on to finish. This one will be much more, a little bit complicated. Take some time to digest this. When you say onto, you cannot run away from stating the domain and codomain. And in any question of function, I must state what is the domain and also what is the codomain. Okay, my okay. The moral of the story is that domain is really important. This question, this specific question, if I put another value of codomain, katakan ayo kacau lah ni. Hide. Jap. Hide. Baru nampak. Okay, if I change this question slightly to a real number it means that it includes fraction as well. This one, for this kind of 2x plus 2, it will be on 2 this time. But you prove it on your own later. Be sensitive with the domain and codomain. If I change this question, instead of z here to r, this conclusion will be on 2 already. And please verify. I will show you one more question of on 2. This time it involves x squared. Okay. Let f z to z such that fx equals to x squared. Alright, is this on 2? This time it will be quite simple as well, but the proof is like that as well. Like just now, definition ingat balik. For every y from B, saya buka, from the codomain there is such x, from the domain such that fx equals to y. Okay, for this question, let's see. If I let fx equals to 5, the question, is there an x from the integer domain here such that fx equals to 5? Ada tak? Is there any integer? When you square, it will be 5. Some of you may say, there is no integer. How to write it? This is a very clever way to write this. The proof start now. Let fx equals to 5, then x squared equals to 5. What is x? X is plus minus square root of 5. To link this, so this statement, there exists x is an integer. My counter proof is that this is not an integer. The square root of plus minus square root of 5 is definitely not integer. As my conclusion, if fx equals to 5, there does not exist an element from the valid integer fx equals to 5. As my conclusion, for the case of fx equals to x squared is not onto. Finish. Any question before I take a break? Oh yeah, some of your friends say that you have quiz. If you have something, yeah, you can quit this lecture and look at the online afterwards. Huh? If you don't have question, I let you to take a break for only 2 minutes. 2 minutes starts now. Yeah, why we having a break? Last time I show you a Daruma dog. No, I show you a apa nama tu? Something from Japan. I don't remember what your friend said. This is also from Japan. This is also known as Daruma doll. Who reads Doraemon also know this. This is basically a puppet, a toy, patung which will always stand up when it's being thrown. Saya cuba tunjuk, boleh tak nampak? Tak naik, okey tak jadi, tak rata. Okay, this Daruma doll is really cannot stand up back. Sepatutnya, okay, like this, dia boleh berdiri kan? Tu pun dia nak berdiri tu. Okay, if you read about Daruma doll, is some dia penat. Pandai ke kau kan? The bigger the Daruma doll, more likely dia akan bangun balik lah. Okay, but the legend is about some legend Daruma ni lah. It's a tradition. The eyes is not being colored. It says that when you have a wish, you color one eye, and then when your wish is already come true, you color the other eye. This one is also my friend give it to buy it for me. Tu dia bangun balik. You tak nampak lah. Saya tak nak tunjuk meja saya sangat. My table is so messy. I wish this is not my table anymore. Okay, sangat banyak. Dengan attendance lama korang lah, dengan quiz korang lah, dengan kerja lain lah. So I will not show you my table. Then the 2 minutes is over. We continue back with a little bit more, maybe 15 minutes, I hope so. Until 2:30 I take your time. Present screen. Okay, this is about mathematical induction. I ought to teach you also today, but I don't do yet the induction. So please be patient with me. I'm sorry because, like I said, I need to do some chores as well, not only your lecture. But I will try to do my best. If I have time, I will do it. Huh? Mana ni? You presenting the screen. Okay, present now. I promise you that I will do extra class. Especially when you are near your exam. Okay. But don't use that statement as your reason you don't attend my class. Ha? Mana tahu lepas ni, oh tak payahlah pergi kelas. Nanti sir pun buat extra class. Extra class lah. Okay. Okay, math induction. Okay, maybe it's a little bit of introduction. Yeah. I will start first with motivation. This story I always tell my students every semester. Once upon a time ago, there is a young boy, age 12. The teacher asked this, what is the sum what is the sum from 1 until 100? This boy actually exists 200 years ago. That boy managed to answer this question very fast. According to the legend, he answered it within 1 minute. The boy said that he realized this pattern. 1 plus 100 is 101. 2 plus 99 is 101. 3 plus 98 is 101. How many 101s are there? Siapa ni? Wah, 50-50. Hebatlah Adam Pang. Yeah, you are correct maybe. Let's show. I tried to prove this statement. The boy presumes that this summation will until 50 plus 51. So basically, it will be 50 times 101. So the answer will be, like Adam Pang said, it will be 50-50. And if you translate this formula, there is the same as 50 times, saya lupa, over 2. 51, sama ke? Sekejap. Ni saya tak pasti pula. Sekejap. And, saya kena tengok formula. Okay. It will be same like n plus 1 over 2. Yeah, it will be 50-50. Okay. The boy name is Carl Frederick Gauss. Okay. The Prince of Math. Siapa tulis ni? Chat. Welcome. Welcome apa? Okay. Okay, this is the boy's name is Carl Frederick Gauss. He's a famous mathematician and apparently is known as the father of number theory. Okay, thank you Gauss for showing us this marvelous, seems a hard question, but it's very simple. Gauss only add up 1 until 100. But what if I tell you, you can actually count what is 1 plus 2 plus 3 until 2020? I can answer this quite fast. This year is 2020. What is the summation from 1 until 2020? It's just 2020 times 2021 over 2. So become 110, 110, 2021. Masuk dalam kalkulator sendiri. Can also be answered under not 1 minute, but 10 seconds. And if you extrapolate this idea, you not only can add up 1 until 100, 1 until 20, 20. You can add up 1 plus 2 plus 3 plus a large number that you can ever think of. For example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 200. One integer. You can add up very fast. And suppose this number is infinite, the formula is just n over n plus 1 over 2. This is the formula for every possible integer of n. How do you want to prove something that is infinitely large but still can be summed up to a single integer here? Very interesting, actually. The summation is infinite, but the answer is single integer. This is what you will learn how to prove this theorem, a statement that can be shown to be true or false, that is actually true. Okay, so I will show you one example only today. Although the answer is already there, but like I said, you must know the know-how, the method on how to prove this. This is known as mathematical induction. This is a unique way of proving, because suppose you have an infinite ladder, tangga, a very high ladder that you cannot reach the top. But the way of using mathematical induction is that you assume that the first step can be step, like this guy here. You believe that the case of k is true, and you prove that k plus 1 is true, therefore you can reach the top, like the previous sum. Okay, although this slide show that it's a 4-step, actually it's just, I always tell my student, that is actually a 3-step. The last step is just a conclusion. So I want you to remember 3 steps, because conclusion must be there for every proof, right? So it's a basic, it's not a step for me. The first step is that proof the first base case and not is true. And not is not necessarily 1. You must look at the domain. And not, it means the first value of the given set domain. Second, you assume that some k is true. Assume, don't prove. Assume, you believe. And by using assumption 2, you need to prove p k plus 1 is true. Okay, I spice up a little bit with this statement, because to use to prove math induction, please use assumption from step 2. Do not ever forget that, because my students tend to forget that. They don't use the assumption. That's very wrong. Now, I will show you the example. Okay. Proof by using mathematical induction 1 plus 2 plus 3 plus blah 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 until n is equal to n plus 1 over 2. I want to prove that the Gauss trick is true. Then, first step, what is the first value here? Is this. If you write this correctly, this case n is a natural number. It means that n is the positive integer, natural number. Therefore, n equals to n not equals to 1. I must prove that P1 is true. I will show you left-hand side, right-hand side. Right-hand side is this formula. right hand side. This whole bunch of sum is left hand side. Okay, clear? What is left hand side? Left hand side for this case is 1. Because 1, only 1, you tak tambah, you don't add, just 1. For right hand side is a different thing. You must put into the formula 1 plus 1 over 2, which is 1. For this case, left hand side equals to right hand side for P1. P1 is proven to be true. Very easy. Now we proceed with step 2. Step 2, you don't prove, you assume PK is true. This is the case where n equals to k. So I believe 1 plus 2 until k is believed to be k plus 1 over 2. That's all on step 2. You don't prove, I believe, that the summation of 1 until k will be k times k plus 1 over 2. Not really hard. But the last step, pk plus 1 is true. N equals to k plus 1. This is a different story. 1 plus 2 plus 3 will arrive at k. After k is integer k plus 1. I must show that it will be kanan, the right hand side, will be k plus 1. This is 1 k plus 1 plus 1. Okay. Plus 1 over 2. So what is my left hand side? What is my right hand side? For the time being, I don't see it equal yet. You can start either way by left hand side or right hand side. Depends on you. Yeah, the important thing is that it will be equal. Right now, right hand side is very simple because I can see it will be k plus 1, k plus 2 over 2. Left hand side. How to prove this? Just now I said that you must use assumption 2. Assumption from step 2, this one. What is 1 until k? Is that it will be k plus 1 over 2. I take it from step 2 here. I end up with k plus 1. Right now, it does not seem similar yet, so you must prove it. If you master factorization, this will be k plus 1 plus 2k plus 1 over 2. And based on algebra, this one is k plus 1, k plus 2 over 2. Kan sama? Is it equal? As left hand side is equals to right hand side for pk plus 1, I conclude that pk plus 1 is true. As my large conclusion, in the slide is called step 4, right? My large conclusion, actually the any proof must match conclusion, by using math induction, what I proved to you just now is that 1 plus 2 plus 3 until n will be n plus 1 over 2 for every natural number out there. So Gauss is right. And I also proved that this theorem is right. This will be a long proof. You tengok? one page. Then we complete the math induction. How many marks? Usually 10 marks. If you manage to do this very well, you can easily get 10 marks. And what is the use of this theorem? Like just now I said, this happened to be true for every possible natural number. So just now I showed to you the example, what is 1 plus 2 plus 3 plus until 2020, right? Just now. What is the summation? N equals to 2020. Therefore, if I put in the formula, the answer will be 2020 times 2020 plus 1 over 2. The summation from 1 until 2020 is this integer. Put in the calculator. So this is the usage of this theorem after I prove that by using mathematical induction, this is true. Very beautiful. Okay. This will be my last example for today. For next week lecture, I will continue more with induction, and I will start to introduce you with the concept of abstract algebra. So I'll leave you with 2 minutes, 1 to 2 minutes for any question. TikTok. No, not the TikTok. I'm TikTok. TikTok. The clock is counting. Take some time to digest this. Next week, I will show you a more harder example like this one. This left-hand side, yeah, I am waiting for the question, by the way, while I'm talking this. You can see many summation here. The sum of odd integer, like number 3, can be easily as equals to n squared. Wow. It means if I know what is one, ini soalan assignment ke? Ya kot? I tak ingat lah. Soalan assignment even kat kisah lah. 1 plus 3 plus 5 until 2021. Dia mesti odd. It must be odd. What is the formula is n squared? What is n? So the answer will be 1011 squared. Very fast. Sum of odd integers, banyak benda. There is many things that we can prove. There are many beautiful patterns in this world that can be answered very fast. This is the sum of geometric progression at maths. Okay? No question, Betul, Sure, Okay, if no question, thank you so much for attending my lecture. Today is very few people, 41 only, but that's fine. I hope as long as you understand my lecture, and I will be happy about. Ada soalan tak? Okay, tak ada. Okay, I will stop my lecture today, and I see you next week. Goodbye.